Hold two magnets in your hands, push them together, and you feel it. An invisible wall. A force with no visible source acting across empty space. Flip one magnet around, and the sensation reverses. They snap together with a satisfying clack. This is so familiar, so ordinary, that we barely question it anymore. But if you pause and truly ask why, if you dig beneath the comfortable labels we use, you will find yourself standing at the edge of one of the deepest mysteries in all of physics. Richard Feynman knew this. He spent a lifetime explaining the universe, and when it came to magnets, he did something most scientists avoid. He admitted that at the most fundamental level, we do not know why. We know what magnets do. We can predict their behavior with staggering precision, but the why, the reason they exist and behave this way, leads to a chain of questions that ultimately has no bottom. Let's start with the experience. When you push two magnets together and feel resistance, what exactly are you feeling? The tempting answer is to say there is a magnetic force between them. But that is just a label. It does not explain anything. It is like saying a sleeping pill works because it has dormative properties. You have renamed the mystery without solving it. To truly explain the magnetic force, you would need to describe it in terms of something more fundamental, something you already understand. But here is the problem. The magnetic force is already one of the most fundamental things there is. It is not built from simpler parts. It is a bedrock feature of reality. And that means any attempt to explain it will either be circular or will simply push the mystery one level deeper. Consider what happens when people try. You might say magnets work because of magnetic fields. Fine, but what is a field? It is a region of space where a force acts. That is just another way of saying there is a force. You have introduced a new word, but not a new understanding. You might go further and say the field is made of virtual photons, particles that carry the electromagnetic interaction. This is closer to the truth, but now the question shifts. What is a virtual photon? Why does exchanging particles create a force? And we are back where we started, just with more sophisticated vocabulary. Feynman understood this deeply. He famously gave an interview where he was asked to explain why magnets attract and repel. He could have rattled off textbook answers. Instead, he stopped and said something honest and profound. He said he could not explain it in a way that would satisfy the questioner because the questioner did not have the prerequisite knowledge of the deeper frameworks. And even if they did, those frameworks do not answer why in any ultimate sense. They only describe how with greater precision. So let's follow the chain. What do we actually know? We know that inside a magnet, vast numbers of electrons have their spins aligned. Electron spin is a quantum mechanical property. It is not literally the electron spinning like a top, though the mathematics resemble angular momentum. It is an intrinsic form of angular momentum that every electron possesses. And crucially, a spinning charged particle generates a magnetic field. In most materials, the spins of electrons point in random directions. Their magnetic effects cancel out. The material is magnetically neutral. But in certain materials like iron, cobalt, and nickel, a quantum mechanical interaction called the exchange interaction favors alignment. Vast numbers of electron spins line up in the same direction within regions called magnetic domains. When these domains are themselves aligned, you have a macroscopic magnet. The individual tiny magnetic contributions from billions of electrons add up, and the result is a field you can feel centimeters away. That is the mechanism. But it still does not answer the deeper question. Why does a spinning charged particle create a magnetic field? Here we enter the realm of electromagnetism, one of the four fundamental forces. In the mid-19th century, James Clerk Maxwell unified electricity and magnetism into a single framework. He showed that a moving electric charge creates a magnetic field, and a changing magnetic field creates an electric field. These two phenomena are inseparable aspects of a single entity, the electromagnetic field. This was a monumental insight. It revealed that electricity and magnetism are not separate forces, but two perspectives on one underlying reality. Light itself is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields propagating through space. Every color you see, every radio wave, every X-ray, is electromagnetism in action. Maxwell's equations describe all of this with breathtaking elegance and accuracy. But they do not explain why the electromagnetic field exists. They tell you how it behaves. They give you rules. Change an electric field here and a magnetic field appears there. The equations are deterministic and precise. You can calculate the magnetic field around a current-carrying wire or the force between two magnets with exquisite accuracy. Engineers use these equations to design motors, generators, transformers, and the entire electrical grid. The theory works, but it does not answer why the universe has this field, why it obeys these particular equations, or why electric charge exists in the first place. Go deeper still. In the 20th century, quantum mechanics revolutionized our understanding. The electromagnetic force, we now know, is mediated by particles called photons. When two electrons repel each other, the interaction is not a spooky action at a distance. It is an exchange. One electron emits a photon, the other absorbs it. This exchange of momentum and energy is the force. But these are not ordinary photons. They are virtual photons, entities that exist only fleetingly in the mathematical description of the interaction. They do not obey the usual energy-momentum relationship. They can have properties that would be forbidden for a real photon. They are mathematical intermediaries, essential to the calculation but never directly observed. If you try to observe them, they vanish. The force is real. The virtual photon is a feature of the quantum mechanical description, a necessity of the theory, but not something you can put in a box. Richard Feynman formalized this with his diagrams and his path integral approach. In quantum electrodynamics, every interaction is a sum over all possible ways it could happen. An electron emitting and absorbing photons, photons splitting into particle-antiparticle pairs for an instant, all of these virtual processes contribute. The final observable outcome is the sum of infinite possibilities, most of which cancel out, leaving the measurable force. This framework is astonishingly successful. QED predicts the magnetic properties of the electron to 12 decimal places. It is the most precisely tested theory in all of science. And yet, for all that precision, it does not tell you why. It tells you that if you have electric charge, then photons mediate the force. And here is how to calculate it. But why does charge exist? Why is the photon massless? Why does the interaction strength have the value it has? That interaction strength is set by a number called the fine structure constant, approximately 1 over 137. This dimensionless number appears throughout physics. It sets the scale of atomic energy levels, the speed of light in relation to atomic physics, and the strength of the electromagnetic force. Change it even slightly, and atoms fall apart or never form. Chemistry becomes impossible. Life cannot exist. We can measure this number to extraordinary precision, but we have no theory that predicts its value. It is an input, a dial on the universe that is set to 1 over 137 for reasons we do not understand. Feynman called this one of the great damn mysteries of physics. He was haunted by it. Here was a number, fundamental to everything, and we had no idea why it was what it was. Now let's return to the magnets in your hand. When you feel them push apart or pull together, what are you actually feeling? You are feeling the electromagnetic force, one of the fundamental interactions, mediated by virtual photon exchanges between the aligned electron spins in one magnet and those in the other. The force is transmitted across the space between them by the field. But the field is not a substance. It is a mathematical description of how test charges would respond at every point in space. The force you feel is the cumulative effect of countless quantum interactions happening at the level of individual electrons and photons, scaled up to the macroscopic world. It is a statistical aggregate of the quantum realm made tangible. But notice what has happened. I have described the force in terms of electrons, photons, fields, quantum mechanics, and Maxwell's equations. I have used the most successful and accurate framework physics has ever produced. And yet, I have not told you why magnets work. I have told you how, in increasingly sophisticated language. The why keeps receding. Why do electrons have spin? Because they are fundamental particles, and spin is an intrinsic quantum property. Why do charged particles create fields? Because that is how electromagnetism works. Why does electromagnetism exist? Because it is one of the fundamental forces. Why are there fundamental forces? We do not know. We have reached the end of the explanatory chain. Beyond this point, there are only descriptions, mathematical models that work, and unanswered questions about why the universe has these particular rules. Feynman was brutally honest about this. He pointed out that when you ask why, you are implicitly asking for an explanation in terms of something familiar. But the deepest truths of physics are not familiar. They are the foundation upon which familiarity is built. You cannot explain them in simpler terms because there are no simpler terms. You can only describe them with mathematics and observe that the universe behaves this way. The equations work, the predictions match experiments. That is all we have. And it is both incredibly powerful and profoundly humbling. There is another twist. The force you feel when you push magnets together is not unique to magnets. It is the same force that gives solidity to matter. When you press your hand against a table, you feel resistance. That resistance is electromagnetic. The electrons in the atoms of your skin and the electrons in the atoms of the table repel each other. The force is immense. In fact, the electromagnetic force is roughly 10 to the power of 40 times stronger than gravity. That is a number so large it is meaningless to human intuition. If you and another person each had just 1% more electrons than protons in your bodies, the electromagnetic repulsion between you would be enough to lift the entire Earth. But you do not feel this because matter is electrically neutral. Every positive charge is balanced by a negative charge with exquisite precision. The titanic forces cancel out almost perfectly, and what remains is the gentle residue we experience as the solidity of objects and the pull of gravity. The magnet is special only because it allows you to feel the electromagnetic force at a distance, unshielded by the usual neutrality. Inside the magnet, the electron spins are coordinated, their fields add up instead of cancelling out. The result is a macroscopic field you can sense with your hands. It is the same force that holds atoms together, that allows chemistry to happen, that powers the sun through nuclear fusion by overcoming electromagnetic repulsion, and that transmits light across the cosmos. Magnetism is not a separate phenomenon. It is a manifestation of electromagnetism, which is itself one facet of the unified electromagnetic interaction. And all of this traces back to the existence of electric charge and the laws governing how charges interact. But why does charge exist? Why does like repel like and unlike attract? These are the axioms of electromagnetism. They are not derived from anything deeper. They are the starting point. In physics, we always hit this wall. Every explanation relies on premises, and those premises are either accepted as fundamental or explained in terms of other premises. Eventually, you reach the ground floor, the fundamental laws and constants, and there the questioning must stop. Not because we are lazy or incurious, but because we have reached the limits of what explanation means within the framework of science. Science describes patterns. It finds regularities, formulates laws, and makes predictions. It does not answer why those laws exist in the first place. That is a question of metaphysics or philosophy, not physics. Feynman embraced this boundary. He did not see it as a failure. He saw it as a feature of intellectual honesty. Physics reveals how the universe works with stunning clarity. It gives us power to manipulate nature, to build technologies, to predict eclipses and design microchips. But it does not, and perhaps cannot, answer the ultimate why. The universe simply is this way. The laws are what they are. The constants have the values they have. We can explore, measure, calculate, and marvel. But the final why remains out of reach. And that, Feynman would say, is not a reason for despair. It is an invitation to humility and wonder. The mystery is not a bug. It is the most profound feature of existence. So when you hold those two magnets and feel them push or pull, you are touching one of the universe's fundamental forces. You are feeling the electromagnetic interaction, mediated by quantum fields and virtual photons, arising from the alignment of electron spins, governed by laws we can describe but not ultimately justify. The force is real. The equations are precise. The predictions are flawless. But the reason it exists, the why behind the what, is a question that leads not to an answer, but to the edge of knowledge itself. And standing at that edge, confronting the limits of understanding, is where physics becomes not just a science, but a profound encounter with the mystery of being.